Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind, to step away from screens and deadlines in the relentless rush of now and step quietly into the vast, starlit corridors of cosmic history, where time stretches back not thousands of years but billions, where the story isn't written in clay tablets or stone monuments, but in the light of distant galaxies still travelling toward us across the void. Here, in this space between present and primordial, we wander together through one of the most astonishing possibilities modern physics has ever proposed. We explore the idea that our entire universe, everything we see and know, might exist inside a black hole. It sounds impossible, like something from science fiction, but the scientists who study such things have found reasons to take this seriously. Not because it's dramatic, though it certainly feels that way, but because when we follow the mathematics and the evidence as far as they'll go, this strange picture of reality begins to take shape. Each episode here isn't just about equations and theories. It's not about memorizing cosmological constants or cataloguing distant objects. It's about the human desire to understand our origins, the scientists dedicating lifetimes to questions that may not have answers, the observations capturing patterns older than Earth itself. It's about one of the most profound frontiers humanity has ever explored, where horizons bend backward, where universes nest inside one another, and where everything we thought we knew about cosmic beginnings is being quietly, beautifully reconsidered. If you enjoy these quiet journeys beyond our world, a like and subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. The story begins not in deep space, but in observatories scattered across Earth, places where scientists peer into the darkness and measure light from galaxies billions of years in the past. It starts in university offices where physicists write equations on whiteboards, trying to understand gravity at its most extreme. It begins with Albert Einstein, working in a patent office in Bern, Switzerland in 1905, developing theories that would reshape our understanding of space and time. Einstein gave us general relativity, the framework that describes how massive objects curve the fabric of space-time itself. His equations predicted phenomena so strange that even he doubted them. Among these predictions were black holes, regions where gravity becomes so strong that not even light can escape. For decades, black holes remained mathematical curiosities, solutions to equations that seem too extreme to exist in nature. Many physicists, Einstein included, believed the universe would find a way to prevent such objects from forming. But as telescopes improved and observations accumulated, evidence mounted. Astronomers noticed stars orbiting invisible objects at incredible speeds, saw jets of matter streaming from galactic centers, detected X-rays from gas spiraling into darkness. By the late 20th century, black holes were no longer theoretical. They were real, observable, and scattered throughout the cosmos. The setting shifted dramatically in 2015 when scientists at the Laser Interferometer Gravitational Wave Observatory detected ripples in space-time itself, gravitational waves produced by two black holes colliding more than 1 billion light-years away. This wasn't indirect evidence, it was direct confirmation. Black holes existed, they merged, and they warped reality around them. The detection opened a new window on the universe, allowing scientists to observe events previously hidden from view. It marked the beginning of a new era in astronomy, one where black holes moved from the edges of theory into the center of cosmic understanding. Around the same time, cosmologists studying the universe's expansion made increasingly precise measurements of its size, age, and evolution. They mapped the cosmic microwave background, the faint afterglow of the Big Bang, and found patterns suggesting the universe had undergone rapid expansion in its earliest moments. They measured distances to far galaxies and discovered that space itself is accelerating outward, pushed by a mysterious force called dark energy. These observations painted a picture of a universe that began in a hot, dense state and has been expanding ever since, growing colder and more diffuse with time. It was in this setting, with black holes confirmed and cosmic expansion measured, that scientists began noticing something peculiar. The mathematics describing the interior of a black hole looked remarkably similar to the mathematics describing our expanding universe. Both involved horizons beyond which information cannot pass. Both featured singularities where known physics breaks down. Both showed space-time stretching in specific, predictable ways. The parallels were too striking to ignore. If black holes were real, and if their interiors could contain expanding regions of space, then perhaps our universe was such a region. Perhaps we were already living inside one. This possibility emerged not from wild speculation, but from careful comparison of equations and observations. The setting was rigorous science, laboratories and telescopes, data and theory. It was cosmologists asking what the Big Bang really was, physicists wondering where black holes lead, astronomers measuring expansion rates and finding puzzles in the data. The stage was set not by imagination alone, but by evidence, by the slow accumulation of clues suggesting that reality might be stranger than anyone had dared to think. The question was no longer whether black holes existed. The question became whether we existed inside one. The observatories where this story unfolds are not just buildings with telescopes. They are outposts of human curiosity, places where people spend careers staring at screens, analysing data, and piecing together the history of everything. Some are perched on remote mountain tops where the air is thin and the skies are dark. Others are satellites orbiting Earth, above the atmosphere's distorting haze. Still others are vast underground facilities, designed to detect the faintest vibrations in space-time. Each contributes a piece to the larger puzzle. In these places, scientists work with instruments of astonishing sensitivity. Gravitational wave detectors measure changes in distance smaller than a fraction of an atomic nucleus. Telescopes capture photons that have travelled for billions of years, carrying information about the universe when it was young. Particle accelerators recreate conditions similar to those moments after the Big Bang, smashing atoms together at speeds approaching light. Every measurement, every observation adds detail to our understanding, and every detail raises new questions. The setting also includes the human element, the researchers who dedicate their lives to understanding the cosmos. They are driven not by immediate practical concerns, but by wonder, by the desire to know how reality works at its deepest levels. They publish papers, attend conferences, debate interpretations, and slowly build consensus. The idea that we might live inside a black hole emerged from this community, from conversations in hallways and lectures in auditoriums, from peer review and skepticism and gradual acceptance that the possibility deserved serious consideration. This is where the story begins, in a world where black holes are real, where cosmic expansion is measured, where equations suggest unsettling possibilities. It is a setting grounded in observation and mathematics, in the patient work of people trying to understand the universe's structure. And it is from this foundation that the mystery deepens, the question crystallizes, and the exploration truly begins. The spark came not from a single observation, but from a gradual realization among theoretical physicists studying the mathematics of black holes and cosmology. In the 1960s and 70s, scientists began solving Einstein's field equations in new ways, exploring what happened inside the event horizon of a black hole. They found that space-time doesn't simply stop at the horizon, it continues, evolving in ways that depend on the black hole's properties. For certain solutions, the interior looked like an expanding region of space, one that could grow and stretch just as our universe does. This was strange enough on its own, but the real revelation came when cosmologists compared these solutions to models of our universe. The equations describing cosmic expansion, the ones that explain why galaxies move apart and why the universe has an age and a horizon, bore an uncanny resemblance to equations describing black hole interiors. Both involved curved space-time. Both featured horizons separating observable regions from unreachable ones. Both included singularities marking the beginning or end of time. The parallels were mathematical, precise, and deeply unsettling. At first, this seemed like mere coincidence. Mathematics often produces similar structures in different contexts without implying any deeper connection. But as physicists examined the parallels more closely, they found details that strengthened the link. The way time behaves inside a black hole, the way space expands, the role of entropy and horizons, all of these matched features of our observable universe. It was as if the cosmos we inhabit had the signature properties of a black hole interior, viewed from the inside. One of the key insights came from studying the event horizon itself. From outside a black hole, the horizon is a boundary beyond which nothing can escape. Light, matter, information, all are trapped inside. But from within, the horizon doesn't look like a wall. It's simply the edge of what can be seen, a limit set by the geometry of space-time. Our universe has a similar feature called the cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. Beyond that horizon, the universe may continue, but it's forever inaccessible to us. This parallel suggested that our cosmic horizon might actually be an event horizon, seen from the inside. The discovery deepened when scientists considered the Big Bang itself. In standard cosmology, the Big Bang is the moment when space and time began, a singularity from which everything emerged. But singularities also appear in black holes at their centers, where matter collapses and space-time curves infinitely. What if these weren't different phenomena, but two perspectives on the same thing? What if the Big Bang was the interior view of a black hole's singularity, the moment when our region of space-time branched off from a larger cosmos? This idea wasn't just philosophical speculation, it emerged from the mathematics. When you solve Einstein's equations for a collapsing star, you get a black hole with a singularity at its core. When you run those equations forward in time from the singularity's perspective, you get an expanding universe. From outside, it looks like collapse. From inside, it looks like creation. The Big Bang and black hole formation might be the same event, seen from different sides of a horizon. The spark of mystery ignited further when physicists realized this could explain puzzling features of our universe. Why does the cosmos have an edge to what we can observe? Because we're inside a bounded structure. Why did the universe begin in such a hot, dense state? Because that's what the interior of a forming black hole looks like. Why does space expand? Because that's the natural evolution of space-time inside such a region. The answers weren't definitive, but they fit together in a way that was hard to ignore. What made this discovery particularly compelling was that it didn't require inventing new physics. It came directly from Einstein's equations, the same ones that had been tested and confirmed countless times. Black holes were real. Cosmic expansion was real. The mathematics connected them. The spark wasn't a wild guess, but a logical conclusion drawn from established science. It suggested that the universe we see might not be the whole story, that there could be a larger structure outside our horizon, one we can never directly observe, but whose existence explains what we do see. This realization spread slowly through the physics community. Papers were published with titles like Black Hole Cosmology and Universe as the Interior of a Black Hole. Conferences featured talks exploring the implications. Not everyone accepted the idea, but enough did to make it a serious topic of research. The spark had been lit. The mystery was no longer whether black holes could contain universes, but whether our universe was such a case. The evidence wasn't conclusive, but it was suggestive, and that was enough to drive the investigation forward. The discovery also raised profound questions about the nature of reality. If we're inside a black hole, then everything we see, every galaxy, every star, every particle exists within a bounded structure. The universe isn't infinite and unbounded as we might have assumed. It has edges hidden from us by horizons, but real nonetheless. This doesn't change our daily experience, but it changes the context of existence. We're not in an isolated cosmos, but potentially in one bubble among many, each formed inside black holes, each expanding according to the same laws. For scientists, this was both thrilling and humbling. Thrilling because it suggested a grand structure to reality, a nested hierarchy of universes connected by black holes and horizons. Humbling because it meant our universe, vast as it is, might be just one small part of something larger. The spark of mystery came from this tension between what we can see and what might lie beyond, between the familiar expansion of galaxies and the possibility that all of it happens inside the event horizon of an unimaginably large black hole in another realm. This was the discovery that set everything in motion, the realization that turned black holes from cosmic oddities into potential keys to understanding our very existence. When the idea first surfaced in academic papers and conference halls, the response was divided. Some physicists felt a rush of recognition, as if a puzzle piece had suddenly clicked into place. Others reacted with skepticism, dismissing it as mathematical abstraction disconnected from physical reality. The notion that our entire universe might exist inside a black hole was so vast, so counterintuitive, that even scientists comfortable with relativity and quantum mechanics found it difficult to accept. The first response wasn't uniform. It was a mixture of awe, disbelief, curiosity, and resistance. For those who felt awe, the reaction came from seeing how elegantly the pieces fit together. The equations didn't lie. The parallels between black hole interiors and our expanding cosmos weren't forced or contrived. They emerged naturally from general relativity, the theory that had already explained planetary orbits, gravitational lensing, and time dilation. If the same mathematics that predicted these confirmed phenomena also suggested we live inside a black hole, then the possibility demanded serious attention. These scientists didn't claim certainty, but they recognized that dismissing the idea too quickly would be intellectually dishonest. The mathematics spoke, and they listened. The awe also came from the philosophical implications. If true, it meant that creation wasn't a singular event, but an ongoing process. Every black hole in our universe might be giving birth to new universes, each with its own history, its own galaxies, its own potential for life. Our Big Bang would be one such birth, the moment when our region of space-time branched off from a parent cosmos. This wasn't just a new model of cosmology, it was a complete reimagining of existence itself. To contemplate it was to step outside the familiar framework and see reality as something far grander, far stranger than previously imagined. But alongside awe came disbelief. Many scientists pointed out that the idea, while mathematically interesting, was untestable. We cannot see beyond our cosmic horizon. We cannot observe the parent universe, if one exists. We cannot conduct experiments to confirm or refute the hypothesis. In science, ideas that cannot be tested, no matter how elegant, remain speculations. Some argued that proposing we live inside a black hole was stepping beyond the bounds of science into metaphysics, a realm of ideas that might be internally consistent but couldn't be verified by observation or experiment. This skepticism wasn't mere stubbornness. It came from a legitimate concern about the scientific method. Science advances by making predictions that can be tested, by comparing theory to observation, by allowing nature to confirm or contradict our ideas. The claim that we live inside a black hole seemed to offer no such test. If we're inside, we're trapped inside. The horizon prevents us from seeing out. The singularity lies in our past, unreachable and unobservable. What experiment could possibly settle the question? Without testability, some argued, the idea was more philosophy than physics. Yet others countered that testability isn't always direct. We cannot visit the center of the sun, but we know what happens there because our models predict the sun's brightness, spectrum, and neutrino output. We cannot travel to distant galaxies, but we infer their properties from light. Science often works indirectly, building confidence through consistency rather than direct observation. If the black hole universe model explained features of our cosmos that other models struggled with, then it would gain credibility even without direct proof. The key was finding observable consequences, subtle signatures that would distinguish this scenario from alternatives. The debate also touched on the nature of reality itself. If we're inside a black hole, does it change anything about our daily lives? Does it alter the laws of physics we use, the way stars shine, the chemistry that makes life possible? The answer seemed to be no. From the inside, everything would appear normal. The laws would be the same. The expansion would continue. Life would unfold without interruption. In a sense, whether or not we're inside a black hole was a question about context, not content. It mattered for understanding where we came from and how we fit into a larger structure, but it didn't change the immediate reality we experience. This realization led to different emotional responses. Some found it liberating, a reminder that the universe's grand architecture exists independently of human concerns. Whether we live inside a black hole or not, The stars still shine, the seasons still turn, and life still has meaning. The question became one of curiosity rather than consequence. Others found it unsettling precisely because it seemed to make no difference. If the truth about our cosmic origins doesn't change anything observable, does it matter? Is it even meaningful to ask? Human reactions extended beyond professional scientists. When the idea filtered into popular science articles, documentaries, and online discussions, public responses ranged from fascination to confusion. Many people struggled with the concept itself. How can a universe be inside a black hole when black holes are inside the universe? The apparent paradox stemmed from thinking of black holes as objects floating in space, rather than as structures in space-time. The black hole we might inhabit would be in a different space, a parent universe beyond our horizon. Our universe would be the interior of that structure, separated by the event horizon from the outside. The first response then was not a single reaction, but a spectrum. Awe at the mathematical elegance and cosmic implications, disbelief rooted in concerns about testability and scientific rigor, curiosity about what observable predictions might follow, confusion about what it would mean to live inside such a structure, and underneath it all, a deeper wonder at the strangeness of reality. The possibility that existence is layered and nested in ways we're only beginning to glimpse. This mix of responses didn't settle the question. It opened the door to deeper investigation. Scientists who felt awe began exploring the implications, searching for consequences that could be tested. Skeptics demanded more rigor, pushing for clear predictions that would distinguish the hypothesis from alternatives. The conversation shifted from whether the idea was crazy to whether it was correct, or at least whether it was useful for understanding features of our universe. The first response, divided as it was, marked the transition from discovery to investigation. The spark had ignited debate, and that debate would drive the pursuit of truth forward. At the heart of the black hole universe idea lies a contradiction, a tension between what we observe and what we assume reality must be. Our entire scientific framework is built on the principle that the universe is understandable, that patterns can be measured, that laws can be discovered and tested. Yet, here was a hypothesis suggesting that our cosmos exists inside a structure we can never observe from the outside, bounded by horizons we can never cross, birthed from a singularity we can never directly study. It challenged the assumption that all truths are accessible to investigation. It forced scientists to confront the limits of knowledge. The contradiction appears immediately when we consider horizons. In our universe, we observe a cosmic horizon, the boundary beyond which light hasn't had time to reach us since the Big Bang. This horizon is usually thought of as a consequence of the universe's finite age combined with the finite speed of light. It's an observational limit, not a fundamental boundary. Given enough time, light from beyond should eventually reach us. But if our cosmic horizon is actually an event horizon, the boundary of a black hole interior, then it's not just an observational limit. It's a fundamental feature of space-time. Nothing from beyond can ever reach us, not because we haven't waited long enough, but because the geometry of reality forbids it. This distinction matters because it changes what we can know. In a standard cosmology, the universe beyond our horizon exists, and is in principle accessible given infinite time. In a black hole cosmology, the exterior is cut off forever. We're sealed inside, not by distance but by structure. The contradiction is between the idea that reality is open and explorable, and the possibility that we live in a bounded, enclosed system. Both perspectives are mathematically valid, but they imply different universes. Another contradiction emerges when we think about the Big Bang. Standard cosmology treats it as the beginning of everything, the moment when space and time themselves came into existence. There's nothing before it, because time itself began there. But if our universe is inside a black hole, then the Big Bang wasn't the absolute beginning. It was the moment when our region of space-time branched off from a parent cosmos. Time in our universe began then, but time in the larger structure continued. The singularity we call the Big Bang would be the interior view of a collapse happening in another realm. This shifts the Big Bang from an ultimate origin to a relative one, from the start of everything to the start of our particular bubble. This contradiction between absolute and relative origins is difficult to reconcile, If the Big Bang is just one event among many, if universes are constantly being born inside black holes, then creation becomes commonplace rather than unique. The specialness of our beginning dissolves. Some find this unsettling because it removes the sense of a singular cosmic event. Others find it liberating because it suggests that existence is more robust, more enduring than a single fragile origin. The contradiction isn't about facts, but about meaning, about what it implies for our place in reality. The tension between science and mystery also appears in the role of singularities. In general relativity, singularities are points where the equations break down, where density and curvature become infinite, and where physics as we know it ceases to apply. They're signals that our theories are incomplete, yet they appear inevitably in both black hole and Big Bang models. Science teaches us to seek explanations, to find laws that govern phenomena. But singularities are places where explanations end, where laws fail. They represent the limits of scientific knowledge. If we live inside a black hole, then our existence is bounded by singularities, one in our past at the Big Bang, others potentially in our future if the universe eventually collapses. These singularities are not just mathematical abstractions. They're real features of space-time that shape our history and fate. Yet we cannot study them directly because our physics doesn't work there. This is the contradiction. The most important moments in our cosmic story are the ones we understand least. The mystery isn't separate from science, it's embedded in the science itself. The contradiction deepens when we consider what lies beyond our horizon. If we're inside a black hole, then outside there exists a parent universe with its own stars, galaxies, and possibly civilizations. They would see our universe not as a vast cosmos, but as a black hole, a compact object defined by mass and spin. From their perspective, we don't exist as an observable reality. We're hidden behind the event horizon, our entire history compressed into what looks like a moment of collapse. Meanwhile, from our perspective, they don't exist at all. We see only our own universe, expanding and evolving. Both perspectives are valid, but they're completely disconnected. This is the contradiction of mutual invisibility, two realities sharing a connection through a horizon, yet unable to communicate or confirm each other's existence. Science thrives on verification, on comparing predictions to observations, on testing hypotheses against nature. But how do you test a hypothesis about something you can never observe? The black hole universe idea sits uncomfortably at this boundary. It's derived from established physics, from equations that have passed countless tests. Yet, it makes claims about regions forever beyond our reach. This is the contradiction between derivation and verification, between what mathematics suggests and what experiments can confirm. Some scientists respond to this contradiction by embracing it. They argue that science has always pushed against the limits of the observable. We accept that electrons exist, even though we cannot see them directly. We believe in dark matter even though it doesn't emit light. We infer processes inside stars, even though we cannot visit them. The black hole universe hypothesis is an extension of this tradition, using indirect evidence and theoretical consistency to build understanding. The contradiction isn't a flaw, but a feature, a reminder that reality extends beyond what we can directly measure. Others respond by demanding stricter standards. They insist that without testable predictions, the idea remains speculative. The contradiction here is between expanding knowledge and maintaining rigor, between exploring possibilities and preserving scientific discipline. Both sides have valid concerns. Science advances by being bold, by considering ideas that challenge assumptions. But it also advances by being careful, by distinguishing what we know from what we imagine. The contradiction between science and mystery, then, is not resolved. It remains central to the black hole universe hypothesis. The idea emerges from rigorous physics, yet points toward realms we cannot access. It explains observable features of our cosmos, yet implies structures forever hidden. It offers a grand vision of reality, yet resists definitive proof. This tension is what makes the hypothesis both compelling and controversial, a bridge between what we can measure and what we can only wonder about. As the idea that we might live inside a black hole gained attention, scientists didn't simply divide into believers and skeptics. They fragmented into multiple camps, each offering different interpretations, different mechanisms, different visions of what it would mean and how it might work. The theories multiplied, minds divided, and the landscape of cosmology became richer and more complex. What emerged wasn't a single hypothesis, but a family of related ideas, each attempting to reconcile the mathematical parallels with physical reality. One group focused on eternal inflation, the theory that the rapid expansion in the early universe doesn't end everywhere at once, but continues in some regions while stopping in others. Each region that stops inflating becomes a bubble universe, expanding into galaxies and stars. These bubbles are causally disconnected, separated by inflating space. Some physicists propose that black holes could trigger similar processes, that the collapse of matter might initiate inflation inside the event horizon, creating a new expanding region. Our universe could be one such bubble, born not from inflation in empty space, but from collapse in a parent cosmos. Another camp explored the mathematics of Einstein-Rosen bridges, theoretical structures connecting different regions of spacetime. In the 1930s, Einstein and Nathan Rosen showed that black hole solutions could theoretically connect to white holes, hypothetical regions where matter erupts outward instead of falling in. Though unstable and likely unphysical in pure form, the mathematics suggested that black holes might serve as tunnels. Some theorists proposed that the Big Bang could be the white hole end of such a connection, our universe expanding outward from what appears as a black hole in another realm. This model offered a mechanism: collapse on one side, expansion on the other, connected through a singular transition. A third group turned to quantum mechanics and the holographic principle. Black holes are known to have entropy proportional to their horizon area, suggesting that information is encoded on the boundary rather than in the volume. If our universe is inside a black hole, then perhaps all the information describing our three-dimensional cosmos is actually encoded on a two-dimensional surface at the cosmic horizon. We would be living in a hologram, a projection from the boundary. This idea, while strange, had support from string theory and quantum gravity research. It suggested that dimensionality itself might be an illusion, that what feels like depth is actually information structured on a distant surface. Others approached the question through loop quantum gravity, a framework proposing that space is quantized, made of discrete loops rather than being continuous. In this view, singularities don't actually exist. The collapse inside a black hole would reach a minimum scale where quantum geometry prevents further compression. Instead of collapsing to infinite density, matter would bounce, transitioning from contraction to expansion. Our Big Bang could be such a bounce, the moment when a collapsing region in a parent universe rebounded and began expanding as our cosmos. This theory offered testable predictions, subtle signatures in the cosmic microwave background that might distinguish a bounce from a true singularity. A more speculative group explored the idea of cosmological natural selection proposed by physicist Lee Smolin. The hypothesis suggested that universes producing many black holes would spawn more offspring universes, while those producing few would leave fewer descendants. Over countless generations, the multiverse would evolve toward universes like ours, rich in stars and black holes. This wasn't evolution in the biological sense, but a statistical process favoring certain cosmic properties. If true, it would explain why our universe has the parameters it does. We live in a successful universe, one capable of reproducing through black holes. The theory divided minds because it mixed physics with something resembling natural selection, a controversial blend of disciplines. Still others remained skeptical of all these theories. They argued that without direct evidence, any model was essentially unfalsifiable. The parallels between black hole interiors and our universe might be coincidental, a mathematical similarity without physical significance. Alternative explanations existed for cosmic expansion, horizons, and the Big Bang. Invoking black holes as the origin added complexity without necessarily adding explanatory power. These skeptics didn't deny the mathematics, but questioned whether it translated to reality. They demanded predictions that could distinguish the black hole universe model from standard cosmology. Within each camp, further divisions emerged. Some believed our universe was inside a rotating black hole, which would have different properties than a non-rotating one. Others proposed that charge or exotic matter might play a role. Some thought the parent universe had the same laws of physics as ours, while others imagined different constants, different forces, different dimensions. The possibilities multiplied, each with its own mathematical structure and philosophical implications. The division of minds wasn't just about physics, it touched on methodology. Should scientists pursue ideas that cannot be tested directly, or should they limit themselves to hypotheses with clear observational consequences? Should mathematics guide us even into unobservable realms, or should empirical verification remain the ultimate arbiter? Different scientists answered differently, reflecting deeper disagreements about the nature of scientific progress. Despite these divisions, common threads emerged. Nearly all theories agreed that horizons play a crucial role, that singularities mark transitions rather than endings, and that black holes are more than simple dead ends. The mathematics of general relativity, when pushed to its limits, suggested structures richer than previously imagined. Whether those structures correspond to physical reality remained debated, but the equations themselves were not in doubt. They allowed for these possibilities even if they didn't demand them. The theories also shared a humility about knowledge. Each acknowledged limits to what we can observe and understand. Each accepted that reality might extend beyond our horizon in ways we cannot directly verify. The division wasn't between those who knew and those who didn't, but between those who interpreted the same mathematics differently, who valued different types of evidence, who asked different questions about what constitutes explanation. As minds divided, the field became more vibrant. Conferences featured heated debates, academic papers responded to each other with careful arguments, and graduate students found rich territory for research. The division wasn't destructive but generative, producing new ideas, refining old ones, and pushing the boundaries of cosmology. The black hole universe hypothesis, whether ultimately correct or not, had succeeded in making scientists think harder about the nature of reality, the meaning of horizons, and the possibilities hidden in the equations that govern space and time. With theories proposed and minds divided, the scientific community turned to investigation. If our universe might be inside a black hole, then what could we measure to test the idea? What observations would support or challenge it? The pursuit began not with a single grand experiment, but with a methodical examination of cosmic properties, searching for signatures that might distinguish this scenario from alternatives. Astronomers pointed telescopes at the sky, physicists refined their calculations, and cosmologists analyzed data with new questions in mind. The first avenue of investigation focused on the cosmic microwave background, the faint radiation filling the universe, left over from when it was only 380,000 years old. This light carries imprints of the early universe's structure, tiny temperature fluctuations that reveal how matter was distributed. Standard cosmology predicts certain patterns in these fluctuations, based on inflation and the composition of the universe. If our cosmos originated inside a black hole, especially through a quantum bounce rather than a true singularity, the patterns might differ subtly. Researchers began searching for anomalies, unexpected features that could hint at a non-standard origin. Satellites like the Wilkinson Microwave Anisotropy Probe and later the Planck Observatory mapped the microwave background with unprecedented precision. Scientists analyzed the data, looking for deviations from predictions. They found the universe remarkably consistent with standard models, but small puzzles remained. The amplitude of fluctuations at the larger scales didn't quite match expectations. Some regions appeared slightly colder or warmer than predicted. Whether these were signatures of a black hole origin or simply statistical flukes remained unclear. The data neither confirmed nor ruled out the hypothesis, but it provided constraints, narrowing the range of possibilities. Another line of investigation examined cosmic expansion. If our universe is inside a black hole, the expansion rate might show subtle differences from what standard cosmology predicts. Astronomers measured distances to far galaxies using supernovae, bright stellar explosions that serve as cosmic distance markers. They compared these distances to redshifts, the stretching of light caused by expansion. The relationship between distance and redshift reveals how fast the universe expands and whether that rate changes over time. Dark energy, The mysterious force accelerating expansion complicated the picture, but careful measurements allowed scientists to test whether expansion matched predictions or showed anomalies consistent with a black hole interior. The results were intriguing, but not definitive. The universe appeared to be accelerating faster than expected, based on its matter content. This acceleration was attributed to dark energy, but its nature remained unknown. Some theorists proposed that dark energy could be a signature of our universe's status as a black hole interior, a reflection of the parent cosmos's influence. Others argued it was a property of empty space itself, unrelated to black holes. The data didn't settle the question, but it kept the hypothesis alive, showing that expansion had features not fully explained by conventional models. Researchers also investigated the cosmic horizon, the maximum distance from which light can reach us. In standard cosmology, this horizon expands over time as the universe ages and light from more distant regions arrives. But if the horizon is an event horizon, the boundary of a black hole interior, it might behave differently. Scientists calculated whether the horizon's evolution matched predictions for a standard expanding universe, or showed characteristics of an event horizon. The mathematics was complex, involving both general relativity and thermodynamics, but early investigations suggested the two scenarios might produce distinguishable signatures in how the horizon affects observable phenomena. Black holes themselves became objects of intense study. If they create universes, then their properties, formation rates, and distributions might reveal patterns. Astronomers catalogued black holes across different mass ranges, from stellar remnants a few times the Sun's mass to supermassive giants billions of times heavier. They measured how often black holes form, how they merge, and how they affect their surroundings. Gravitational wave observatories detected black hole collisions, providing data on their populations and behaviors. Each observation added detail to our understanding, though none directly confirmed or denied that black holes birth universes. Theoretical investigation proceeded alongside observational work. Physicists developed more sophisticated models of black hole interiors, exploring how matter and energy behave inside the event horizon. They examined whether the conditions there could give rise to inflation, whether quantum effects near singularities could trigger expansion, and whether information about the parent universe might leak into the child cosmos. Some calculations suggested that properties of the parent black hole, like its mass and spin, could imprint themselves on the child universe's cosmological constants. If true, this would mean our universe's fundamental properties reflect the characteristics of the black hole that birthed us. Researchers also pursued the question of entropy. Black holes have enormous entropy tied to their horizon area. Our universe has entropy too, increasing over time as disorder grows. Scientists compared the two, asking whether cosmic entropy matched what you'd expect from a black hole interior. The numbers were suggestive. The universe's entropy seemed consistent with being inside a massive black hole, though the margins of error were large. More precise measurements of cosmic entropy and its growth rate could potentially test the hypothesis, but those measurements proved difficult to make. The pursuit of answers also involved searching for anomalies in particle physics. If our universe inherited properties from the parent cosmos, then fundamental constants like the strength of gravity or the mass of electrons might show subtle correlations unexplained by standard models. Physicists examined whether these constants were truly independent or hinted at deeper connections. Some proposed that certain combinations of constants were too finely tuned to be coincidental, possibly reflecting conditions in a parent universe. Others argued the tuning was simply selection bias. We observe a universe where constants allow life because those are the only universes capable of producing observers. Throughout this investigation, no single piece of evidence emerged as a smoking gun. The black hole universe hypothesis remained difficult to test directly because the defining features, the event horizon and the parent cosmos, lie beyond our observational reach. But indirect evidence accumulated, a collection of puzzles and patterns that the hypothesis could potentially explain. The pursuit wasn't about proving the idea correct, but about determining whether it remained viable, whether observations were consistent with it, and whether it offered insights that alternative models did not. The investigation continues today, with new telescopes, more sensitive detectors, and refined theoretical tools. Scientists haven't settled the question, but they've established that it's a legitimate one, worth pursuing with the same rigor applied to any cosmological hypothesis. The pursuit itself has driven progress, pushing researchers to think more carefully about horizons, singularities, and the limits of knowledge. Whether or not we ultimately confirm that we live inside a black hole, the investigation has already enriched our understanding of what the universe might be. The data didn't arrive in a single dramatic revelation. It accumulated slowly piece by piece, observation by observation, each fragment adding detail to a picture that remained tantalizingly incomplete. Scientists working on the black hole universe hypothesis didn't expect definitive proof. They looked instead for consistency, for clues that would either support the possibility or rule it out. What they found was a collection of observations that neither confirmed nor denied, but suggested that the idea deserved continued attention. One of the most important data sets came from measuring the cosmic microwave background radiation. This faint glow, at a temperature just under 3 degrees above absolute zero, preserves an image of the universe when it was only 380,000 years old. Satellites mapped its temperature across the entire sky, revealing fluctuations at the level of 1 part in 100,000. These tiny variations correspond to density differences in the early universe, seeds that would later grow into galaxies and clusters. The pattern of fluctuations encodes information about the universe's composition, geometry, and history. When cosmologists analysed this data, they found it remarkably consistent with the standard Big Bang model, but with interesting details. The universe appeared spatially flat, meaning parallel lines don't converge or diverge over cosmic distances. This flatness was predicted by inflation, but also consistent with being inside a very large black hole, where the curvature is so gentle as to be nearly imperceptible. The data also showed that ordinary matter makes up only about 5% of the universe's total energy, with dark matter contributing 27%, and dark energy the remaining 68%. These proportions, while measured with precision, remained unexplained by fundamental theory. Some researchers proposed that these proportions might reflect conditions in a parent universe. If our cosmos formed inside a black hole, perhaps the balance of matter and energy was set by the collapse that created us. Dark energy, in particular, looked like a cosmological constant, a term in Einstein's equations that acts like a repulsive force. Its value seemed finely tuned, large enough to accelerate expansion, but small enough that galaxies had time to form. In a multiverse of black hole-spawned universes, each might have different values, and we'd naturally find ourselves in one where the value allows for complexity. The data didn't prove this, but was consistent with it. Another crucial data set involved measuring cosmic expansion directly. Astronomers observed Type Ia supernovae, stellar explosions with a consistent peak brightness that serves as a standard candle for measuring distances. By comparing the apparent brightness of these supernovae at different redshifts, scientists determined how far they were and how fast space was expanding when their light was emitted. The results, announced in 1998, shocked the community. Expansion was accelerating. The universe wasn't just growing, but growing faster over time. This acceleration required an explanation. Dark energy became the leading candidate, but its nature remained mysterious. Some theorists suggested it could be a property of space itself, others that it was a field pervading the universe, still others that it reflected our status as a black hole interior. If we're inside such a structure, perhaps dark energy is the signature of the parent cosmos's influence, a residual effect of the collapse that birthed us. The data allowed this interpretation, but didn't demand it. Dark energy remained an open question, one the black hole hypothesis could potentially address. Gravitational wave detections provided another stream of data. Beginning in 2015, observatories like LIGO and Virgo detected ripples in spacetime caused by colliding black holes and neutron stars. Each detection revealed details about these objects, their masses, spins, and distances. The frequency of black hole mergers was higher than expected, suggesting the universe produces black holes copiously. If each black hole potentially creates a new universe, then the multiverse would be vast, constantly growing as new bubbles branch off. The data on black hole populations didn't prove this, but showed that the raw materials for such a process exist abundantly. Measurements of the cosmic horizon also contributed clues. Observations showed that we can see approximately 46 billion light-years in any direction, despite the universe being only about 13.8 billion years old. This is because space has expanded while light travelled toward us. The horizon isn't a fixed distance, but a growing boundary. Physicists calculated whether this growth matched predictions for a standard expanding universe, or showed characteristics of an event horizon. The calculations were subtle, involving thermodynamics and quantum field theory, but suggested the cosmic horizon shares properties with black hole event horizons, including having temperature and entropy. Data on the distribution of galaxies added another layer. Large-scale surveys mapped millions of galaxies, revealing how matter clusters across cosmic scales. The pattern showed a web-like structure with filaments, walls, and voids. Computer simulations starting from the tiny fluctuations in the microwave background successfully reproduced this structure, but only by including dark matter and dark energy. The fact that our universe has this particular structure, one that requires invisible components to explain, raised questions. If we're inside a black hole, could dark matter be related to the parent universe's influence? Could the web structure reflect conditions at our origin? Particle physics experiments contributed fragments as well. Measurements of fundamental constants, the strength of forces, the masses of particles, revealed values that seemed arbitrary, yet finely tuned. Change any of them significantly, and the universe becomes inhospitable to life. Stars wouldn't form, atoms wouldn't be stable, chemistry wouldn't work. This fine-tuning could be coincidence, or it could suggest our universe is one of many, selected from a larger ensemble because its properties allow observers. The black hole multiverse model provided a mechanism for generating this ensemble, with each black hole producing a child universe with slightly different constants. The data on cosmic entropy also offered clues. Entropy, a measure of disorder, increases over time in our universe. This growth gives time its arrow, the sense of past and future. Scientists calculated the universe's total entropy, dominated by the entropy of black holes within it. The numbers were enormous but finite. Some theorists compared this to the entropy of the universe as a whole, if it were itself a black hole interior. The match wasn't perfect, but it was close enough to be interesting, suggesting that viewing the cosmos as a black hole was mathematically reasonable. What all this data had in common was consistency with the black hole universe hypothesis, without being proof. Every observation could be explained by standard cosmology with dark matter and dark energy, but the black hole model offered an alternative framework that fit equally well. The clues were fragments, pieces of a puzzle that could be assembled in multiple ways. No single piece was decisive, but together they painted a picture of a universe that could plausibly be inside a black hole without contradicting any confirmed observations. The data also highlighted what remained unknown. We still don't know what dark energy is, what dark matter is, why the universe is flat, or why fundamental constants have their values. The black hole hypothesis doesn't answer these questions definitively, but it provides a context where they might make sense, a larger structure where our universe's properties reflect its origin, rather than being inexplicable coincidences. The clues and fragments don't close the case, but keep it open, suggesting that the investigation should continue, and that the truth, whatever it is, lies somewhere in the patterns we've measured and the mysteries that remain. Beneath the question of whether we live inside a black hole lies a deeper mystery, one that reshapes how we think about existence itself. As scientists delved further into the hypothesis, they realized it wasn't just about our universe's origin. It pointed towards something more profound, the possibility that black holes are not endpoints but gateways, that universes reproduce, that creation is an ongoing process, rather than a singular event. This hidden truth, if true, transforms black holes from cosmic curiosities into the engines of reality, the mechanism by which existence perpetuates itself. The deeper mystery emerged when physicists seriously considered what happens inside a black hole. Standard treatments focused on the inevitability of the singularity, the point where matter collapses and space-time curvature becomes infinite. but some solutions to Einstein's equations suggested that the interior might be more complex. Instead of everything compressing to a point, space could expand, forming a new region of spacetime disconnected from the outside. This region would have its own geometry, its own evolution, potentially its own galaxies and stars. From inside, it would look like an entire universe. From outside, it would be invisible, hidden behind the event horizon. This realization meant that every black hole in our universe might contain a cosmos. The stellar mass black holes scattered throughout our galaxy, the supermassive giants at the centers of galaxies, even the microscopic black holes that might have formed in the early universe, all could be universes unto themselves. We cannot see inside them, because horizons prevent information from escaping, but mathematical consistency suggests they exist. If true, the number of universes in reality is staggering, far beyond what inflation or other multiverse theories predicted. The hidden truth went further. If black holes create universes, then our universe, with its own black holes, is creating countless others. Each of those child universes would have its own black holes, spawning yet another generation. The process would continue indefinitely, producing a vast tree of nested realities, each connected to others through horizons and singularities, but forever isolated by the geometry of space-time. Our cosmos would be one branch on this tree, our Big Bang one budding event among countless others. This structure suggested something even more remarkable, that universes evolve, not in the biological sense, but in a process resembling natural selection. Universes that produce many black holes spawn many offspring. Universes that produce few leave fewer descendants. Over countless generations, the multiverse would become dominated by universes like ours, capable of forming stars, creating heavy elements, and generating black holes. Our universe's properties, the ones that seem finely tuned for complexity, might not be coincidental. They might be the result of this cosmic reproduction, selected over time from the ensemble of possibilities. This idea, called cosmological natural selection, was controversial but intriguing. It suggested that the laws of physics we observe, the values of fundamental constants, even the existence of life, might be byproducts of a larger process. Life emerges in universes rich with stars and black holes, because those are the universes most capable of reproducing. We don't live in a special universe designed for us, but in a typical universe within the subset, capable of generating observers. The hidden truth here was that our existence might be explained not by design or coincidence, but by a selection process operating at the largest scale imaginable. The deeper mystery also touched on the nature of information. Black holes are known to have entropy, suggesting they store information. When matter falls into a black hole, does that information disappear, or is it preserved somehow? The holographic principle suggested the latter, proposing that information is encoded on the event horizon rather than being destroyed. If our universe is inside a black hole, then perhaps all the information describing our cosmos is encoded on our cosmic horizon, a two-dimensional surface containing a three-dimensional reality. This would mean dimensionality itself is emergent, that what we experience as depth is actually information arranged on a distant boundary. This hidden truth challenged basic assumptions about reality. If space and time are emergent from information encoded on horizons, then the familiar three-dimensional world is not fundamental. It's a projection, a hologram cast from a boundary we can never reach. Black holes would be the clearest expression of this principle, regions where the holographic nature of reality becomes unavoidable. Our universe, if it's inside one, would inherit this structure, making us participants in a hologram on the grandest scale. Another layer of the deeper mystery involved the singularity itself. In classical general relativity, singularities are places where physics breaks down, where density and curvature become infinite. But quantum mechanics doesn't allow true infinities. Several approaches to quantum gravity suggested that singularities are smoothed out at the smallest scales, replaced by bounces or transitions. If our Big Bang was such a transition, it might not have been a beginning, from nothing but a bounce from a previous state, a moment when a collapsing region in a parent universe rebounded into expansion. This possibility meant that the Big Bang, long thought of as the ultimate origin, was actually a middle point, a transition between one phase and another. The deeper mystery wasn't where everything came from, but how phases connect, how collapse becomes expansion, how endings become beginnings. Black holes would be the mechanism for these transitions, the places where one universe's death becomes another's birth. Creation would be eternal, not because there was no beginning, but because beginnings and endings are local events in an endless cycle. The hidden truth underlying all of this was that reality is far larger than what we observe. Our universe, vast as it appears, might be a small bubble in an ocean of bubbles. The stars we see, the galaxies we map, the cosmic history we trace might all unfold within a structure nested inside others, part of a hierarchy without clear beginning or end. This wasn't speculation divorced from science. It emerged from taking general relativity seriously, from exploring what the equations allow, from following logic into uncomfortable territory. For scientists, confronting this deeper mystery was both humbling and exhilarating. Humbling because it suggested that even the universe, the totality of everything we can see, is not all there is. Exhilarating because it hinted at a structure to reality far grander than previously imagined. The hidden truth was that black holes are not the exotic exceptions to cosmic order, but possibly the rule, the fundamental mechanism by which existence perpetuates itself. If we live inside one, we're not trapped in an anomaly, but participating in the basic process of creation, one generation in an endless chain. Every so often in science, understanding shifts fundamentally. Not because new data contradicts old observations, but because a new framework emerges that explains the same facts in a deeper way. The idea that we might live inside a black hole represented such a potential shift, a turning point in how we conceive of the universe's structure and origins. This wasn't just adding information to existing models, but reconsidering what a universe is, what black holes are, and how the two might be intimately connected. The paradigm shift was subtle, not announced with fanfare, but growing quietly as more scientists considered the implications. The turning point began with the realization that horizons are more fundamental than previously thought. In classical physics, boundaries are where things end, edges that separate inside from outside. But in relativity, horizons are different. They're not physical barriers, but geometric features, surfaces in space-time where light cannot escape. The event horizon of a black hole isn't a place you can touch. It's a limit on causality, a boundary beyond which events cannot influence the outside. The cosmic horizon in our universe plays a similar role, marking the limit of what we can observe. Recognizing that both are fundamentally the same type of structure was the first step in the paradigm shift. This insight led to a new way of thinking about the Big Bang. Instead of treating it as an absolute beginning, physicists began considering it as a horizon crossing, the moment when our region of spacetime separated from a larger structure. The singularity wasn't where everything came from, nothing but where our universe branched off from another. This shift transformed the Big Bang from a unique cosmic event into one instance of a process that might happen continuously throughout a larger reality. Creation wasn't singular but plural, ongoing, embedded in the structure of space-time itself. The paradigm shift accelerated with developments in quantum gravity. For decades, physicists had struggled to reconcile general relativity with quantum mechanics. Relativity described gravity as curved space-time, smooth and continuous. Quantum mechanics described matter and energy as discrete and probabilistic. The two frameworks worked brilliantly in their respective domains, but clashed at extremes. Inside black holes, near singularities, at the Planck scale where space and time themselves might be quantized. The black hole universe hypothesis provided a testing ground for quantum gravity theories. One approach, loop quantum gravity, suggested that space is made of tiny loops woven into a network. At sufficiently small scales, the smoothness of spacetime gives way to a granular structure. In this framework, the singularity at a black hole's core wouldn't be a point of infinite density, but a region where quantum effects dominate, preventing total collapse. Instead, space would bounce, transitioning from contraction to expansion. Our universe's Big Bang could be such a bounce, the moment when quantum geometry turned a collapsing region into an expanding one. This wasn't speculation, but a prediction from the mathematics of quantum gravity. String theory offered another perspective. It proposed that fundamental particles are not points but tiny vibrating strings, and that reality has more dimensions than the 3 of space and 1 of time we experience. The extra dimensions are curled up, too small to detect directly, but they influence physics in observable ways. Black holes in string theory are incredibly rich structures, with properties that depend on how strings and higher dimensional brains interact. Some string theorists propose that our universe might be a brane, a multi-dimensional surface, floating in a higher dimensional space. Black holes could connect different branes, making our universe's origin a feature of this higher dimensional geometry. The holographic principle emerged as a central element of the paradigm shift. It proposed that all information in a volume of space is encoded on the boundary of that volume. For black holes, this meant that everything inside, all the matter and energy that ever fell in, is described by information on the event horizon. The 3-dimensional interior is, in a sense, a projection from the 2-dimensional surface. If our universe is inside a black hole, the same principle applies. Our entire cosmos, with its galaxies and structures, might be encoded on the cosmic horizon. We're living in a hologram, though not in the science fiction sense. The hologram is real. It's just that reality has more structure than our immediate perception suggests. This holographic view changed what it means to exist. If the universe is fundamentally information encoded on a boundary, then space and time are emergent properties, not fundamental entities. They arise from the way information is organized and processed at the horizon. Black holes are the clearest manifestation of this principle, which is why studying them reveals deep truths about reality. The paradigm shift was from thinking of space and time as containers in which events happen to thinking of them as structures emerging from information at boundaries. The turning point also involved rethinking causality. In classical physics, causes precede effects in time. Events are linked by chains of influence stretching back to initial conditions. But in a universe that might be inside a black hole, part of a network of nested realities, causality becomes more complex. The Big Bang, our universe's beginning, would be caused by a collapse in another universe, which in turn had its own causes. Tracing causality backward doesn't lead to a first cause, but to an infinite regress, or a circular structure where universes give rise to one another. This wasn't a philosophical puzzle, but a feature of the mathematics. The paradigm shift was accepting that causality might not have an ultimate origin, that existence might be self-sustaining. For many scientists, this turning point required letting go of comfortable assumptions. The universe is not isolated, the Big Bang is not unique. Space and time are not fundamental, black holes are not dead ends. Each of these realizations challenged intuition, but each followed from taking established physics seriously. The paradigm shift was driven not by new fundamental laws, but by fully embracing the implications of laws already known. General relativity allowed for black hole interiors to be universes. Quantum mechanics required information to be conserved. Together, they pointed toward a reality where universes nest inside black holes, where horizons encode information, and where creation is an ongoing process. The shift also transformed how scientists approached open questions. Dark matter, dark energy, the fine-tuning of constants, the arrow of time, all of these puzzles took on new dimensions in the black hole universe framework. Instead of treating each as an isolated mystery, researchers began seeing them as interconnected features of our status, as a bubble inside a larger structure. Dark energy might reflect the parent cosmos's influence. Dark matter might be related to higher dimensions. Fine-tuning might be explained by selection among many universes. The arrow of time might follow from entropy growth at the cosmic horizon. The paradigm shift was seeing these problems not as separate, but as aspects of a unified picture. Not everyone embraced the shift. Some scientists remained skeptical, arguing that without direct tests, the framework was too speculative. Others worried that it pushed physics into metaphysics, making claims about unobservable realms. But even skeptics acknowledged that the ideas had forced a deeper examination of what we mean by universe, by horizon, by singularity. The turning point wasn't about everyone agreeing, but about everyone thinking more carefully, more rigorously. about the deepest questions. Whether or not we live inside a black hole, the paradigm shift had already enriched physics by showing what's possible when we take our best theories to their logical conclusions. When a paradigm shifts, the immediate ripple spreads through the scientific community like waves from a stone dropped in still water. The idea that we might live inside a black hole, if taken seriously, changed how researchers approached fundamental questions. It didn't happen overnight, and it didn't happen uniformly, but the consequence was real. Cosmology, particle physics, and even philosophy began adjusting to accommodate the possibility. The immediate ripple wasn't about abandoning established science, but about expanding its framework, considering implications that had previously seemed too speculative to pursue. One of the first consequences appeared in how scientists talked about the Big Bang. Textbooks had long described it as the beginning of space and time, the moment when everything emerged from a singularity of infinite density and temperature. This narrative was clean, dramatic, and easy to communicate. But if our universe is inside a black hole, the Big Bang wasn't the absolute beginning. It was a transition, a moment when our region of spacetime separated from a parent cosmos. This shift in language might seem subtle, but it carried profound implications. Questions about what came before the Big Bang, long dismissed as meaningless because time itself began there, suddenly became legitimate. There was a before, though forever hidden from us behind a horizon. This reframing affected research priorities. If the Big Bang was a transition rather than a creation event, then understanding the physics of that transition became crucial. What conditions in a parent universe would lead to the formation of a black hole that births a new cosmos? What role does quantum gravity play at the moment of separation? Can we detect signatures of the parent universe imprinted on our own? These questions drove new theoretical work and motivated searches for subtle anomalies in the cosmic microwave background, small deviations from standard predictions that might hint at our non-standard origin. Another immediate consequence appeared in how physicists thought about black holes themselves. For years, they'd been studied primarily as exotic objects, interesting for testing general relativity and understanding extreme gravity. But if black holes create universes, they became central to existence itself, the mechanism by which reality perpetuates. This elevated their importance, making research into black hole physics not just about understanding one type of object, but about understanding cosmic reproduction. Funding agencies took notice. Proposals to study black hole thermodynamics, information paradoxes, and interior structures received greater attention because they potentially addressed questions about universal origins. The consequence rippled into discussions about the multiverse. Before, multiverse theories came mainly from inflation, the idea that rapid expansion in the early universe created countless bubble regions, each with potentially different properties. The black hole mechanism provided an alternative or complementary pathway to a multiverse. Now scientists had multiple reasons to consider that our universe is one among many. This convergence of different approaches strengthened the case for taking multiverses seriously, even though direct evidence remained elusive. The immediate consequence was a shift from treating multiverses as fringe speculation to treating them as plausible features of reality worth investigating. In particle physics, the consequences were more subtle but still significant. If our universe's fundamental constants reflect conditions in a parent black hole, then attempts to derive those constants from first principles might be misguided. Perhaps the constants aren't determined by deep mathematical necessity, but are contingent on our particular origin. This didn't make particle physics futile, but it suggested that some questions might not have the answers physicists expected. Instead of finding a unique theory that predicts all constants, they might need to accept that our universe is one possibility among many, selected from an ensemble generated by black holes. This prospect was both liberating and frustrating, opening new avenues while closing others. The immediate ripple also touched philosophy of science. If the most important truths about our universe, its origin and context, lie beyond observation, then what does it mean to do science? Traditional scientific method relies on testability, on making predictions that can be confirmed or falsified by experiment. The black hole universe hypothesis seemed to evade this requirement. Its predictions were either about phenomena we already observe, cosmic expansion and horizons, or about regions forever inaccessible beyond our horizon. Some philosophers argued this pushed the idea outside science proper. Others countered that science has always dealt with unobservables, from atoms to dark matter, inferred from indirect evidence. The consequence was a renewed debate about the boundaries of legitimate scientific inquiry. Within cosmology, the immediate consequence was a proliferation of research exploring specific mechanisms. How exactly would a black hole interior give rise to an expanding universe? Different quantum gravity theories offered different answers. Loop quantum cosmology predicted specific signatures in the cosmic microwave background, from the bounce that replaced the singularity. String theory scenarios involving brains colliding in higher dimensions made their own predictions. Researchers developed detailed models, calculated observable consequences, and proposed ways to test them. While none provided definitive proof, the consequence was a richer landscape of ideas, each pushing toward testable predictions. The ripple reached public consciousness as well. Popular science articles, documentaries, and books began featuring the black hole universe idea. Public interest in cosmology surged. People who'd never thought deeply about the Big Bang suddenly engaged with questions about nested realities and cosmic horizons. This broader engagement had consequences for science communication and education. Scientists learned to explain complex ideas in accessible ways, and the public became more comfortable with the notion that reality might be stranger than everyday experience suggests. The immediate consequence was a cultural shift, a growing acceptance that the universe's true nature might defy intuition. In astronomy, the consequence manifested in new observational programs. If black holes create universes, understanding their distribution, formation rates, and properties became even more important. Telescopes searched for intermediate mass black holes, a category between stellar and supermassive that remained poorly understood. Gravitational wave observatories refined their detectors to catch more merger events, each revealing details about black hole populations. Every observation added data that could constrain or support models of cosmic reproduction through black holes. The immediate ripple also affected how young scientists chose research directions. Graduate students and postdocs, seeing established researchers take the black hole universe hypothesis seriously, felt encouraged to pursue related questions. Dissertations explored implications, academic papers proposed tests, and conferences dedicated sessions to the topic. The consequence was a generation of physicists trained to think about universes as nested structures, comfortable with horizons as fundamental features, and skilled in techniques spanning general relativity, quantum field theory, and cosmology. Perhaps the most profound immediate consequence was psychological. For scientists who spent careers studying the cosmos, the possibility that everything we observe exists inside a black hole was simultaneously humbling and exhilarating. Humbling because it suggested the universe, vast beyond comprehension, is merely one bubble in something larger. Exhilarating because it meant reality has layers we're only beginning to glimpse. This emotional consequence, harder to quantify than theoretical developments or observational programs, nonetheless shaped how researchers approached their work. It reminded them that science is not just about accumulating facts, but about expanding the horizon of what seems possible, about maintaining wonder even as understanding grows. The long-term impact of seriously considering we might live inside a black hole extended far beyond immediate research priorities. It resonated through time, influencing how we understand our place in reality, how we teach cosmology, how we approach the deepest questions about existence. The echoes of this idea, whether it ultimately proves correct or not, will shape scientific and philosophical thought for generations. This is because it does more than answer specific questions. It reframes what questions we should ask. One of the lasting impacts is on our conception of cosmic history. Before, the narrative was linear. The Big Bang happened, the universe expanded, galaxies formed, stars ignited, planets coalesced, life emerged. This story placed us at a point along a single timeline, stretching from a singular beginning toward an uncertain future. But if our universe is inside a black hole, cosmic history becomes nested. Our timeline exists within a larger timeline, which might exist within another still. The impact is a shift from linear to branching history, from a single story to countless stories unfolding in parallel, each within its own horizon. This impacts how we teach cosmology to students. The classic presentation of the Big Bang as the origin of everything must be qualified. It's the origin of our observable universe, but perhaps not the origin of existence. Teachers now introduce the possibility that the Big Bang was a local event in a larger multiverse, one instance of a process that happens countless times. Students learn to think about horizons not as distant boundaries, but as fundamental features separating causally disconnected regions. The impact on education is subtle but cumulative, shaping how future generations conceptualize reality. The idea also impacts our approach to fine-tuning, one of cosmology's most perplexing features. The universe's fundamental constants appear finely tuned for complexity. Change the strength of gravity slightly, and stars don't form. Adjust the electromagnetic force, and atoms are unstable. Alter the cosmological constant, and either the universe collapses immediately, or expands too quickly for galaxies to coalesce. This fine-tuning once seemed to require explanation through design or anthropic reasoning. But if black holes create universes with varying constants, fine-tuning becomes expected. We observe a hospitable universe because only such universes produce observers. The impact is philosophical, shifting fine-tuning from mysterious coincidence to natural consequence of cosmic reproduction. Over time, this has influenced debates about existence and purpose. Religious and philosophical traditions have long grappled with why there is something rather than nothing, why the universe permits life, whether existence has meaning. The black hole universe framework doesn't answer these questions definitively, but it provides a naturalistic context where they take on new dimensions. Existence might be eternal, with universes generating universes in an endless chain. Life might emerge naturally in the subset of universes with suitable properties. Purpose might not require external design, but could be inherent in the self-perpetuating structure of nested realities. The impact is on the landscape of ideas available for addressing ancient questions. The long-term impact also appears in how we think about limits of knowledge. Science has historically pushed boundaries, revealing hidden structures from atoms to galaxies. But horizons represent absolute limits, boundaries we cannot cross even in principle. Recognizing this has tempered the optimism that everything is eventually knowable. Some truths, like the nature of the parent universe if one exists, might be forever beyond reach. This doesn't make science futile, but establishes realistic expectations. The impact is a mature understanding that knowledge has frontiers, that some questions might not have accessible answers, and that science must work within these constraints. This realization echoes through philosophy of science, debates about scientific realism, the question of whether our theories describe reality or merely organize observations gain new complexity. If our best theories predict unobservable entities like parent universes, should we believe in them? Traditional empiricism says no, only observable consequences matter. But modern physics, with its successful theories of quarks, black holes, and dark matter, has embraced entities inferred from indirect evidence. The black hole universe hypothesis intensifies this tension. The impact is ongoing philosophical work, clarifying what it means for a theory to be scientific when it makes claims about forever inaccessible regions. The idea's impact on cosmological research is enduring. Decades after it was first proposed, scientists continue refining models, calculating predictions, and searching for signatures. The hypothesis has motivated developments in quantum gravity, encouraged precise measurements of cosmic properties, and inspired creative thinking about testability. Even if ultimately disproven, it will have driven progress by forcing scientists to think rigorously about alternatives. The impact on research methodology is teaching physicists to work with ideas that straddle the line between observable and unobservable, developing tools for indirect inference. Culturally, the impact manifests in how we tell our cosmic story. Science fiction has embraced nested universes, exploring narratives where characters discover their reality is inside a larger structure. These stories reflect back on public understanding, making people more comfortable with counterintuitive ideas. The impact is a cultural shift where the notion of living in a black hole moves from absurd to plausible, where nested realities feel less like fantasy and more like serious possibility. This cultural acceptance, in turn, makes it easier for scientists to pursue such ideas without seeming unserious. The long-term impact also includes what the hypothesis reveals about the nature of scientific progress. Advances don't always come from new observations, but sometimes from reconsidering old ones. The data supporting the black hole universe idea, cosmic expansion, horizons, entropy, was already known. The advance was seeing connections previously overlooked, recognizing that disparate phenomena might be unified in a larger framework. This impact on methodology encourages scientists to periodically revisit established facts with fresh perspectives, asking whether they might fit together differently than assumed. Over time, the impact extends to how we think about our cosmic future. If the universe is inside a black hole, its fate is tied to the black hole's evolution. Will it expand forever, growing cold and empty? Will quantum effects near the horizon alter its trajectory? Will it eventually give rise to new universes through black holes it contains? These questions about the far future gain urgency because they're not just about one cosmos, but potentially about the continuation of existence through reproduction. The impact is making cosmologists think not just about our universe's death, but about what might follow, about whether endings are truly final or transitions to new beginnings. The echoes through time also include inspiration for future discoveries. Just as recognizing we might live in a black hole emerged from fully exploring general relativity's implications, future breakthroughs might come from exploring quantum gravity or other frameworks with equal rigor. The impact is methodological, encouraging thoroughness in following theories to their logical conclusions, even when those conclusions seem strange. History suggests that nature often chooses the stranger possibility and the black hole. Universe hypothesis reminds scientists to remain open to radical ideas grounded in solid mathematics. Ultimately, the lasting impact is on wonder itself. The possibility that we live inside a black hole, that universes nest within universes, that creation is ongoing rather than finished. These ideas kindle the imagination. They remind us that reality is larger and stranger than everyday experience suggests. This sense of wonder, this recognition that the cosmos has depths we're only beginning to fathom, is itself valuable. It drives curiosity, motivates research, and enriches human experience. The impact echoes through time not just in scientific progress, but in sustaining the awe that makes us want to understand our place in existence. Behind every scientific hypothesis are human beings, people who dedicate years or decades to pursuing ideas that might never be fully confirmed. The black hole universe hypothesis is no exception. It exists because physicists and cosmologists, driven by curiosity and wonder, chose to follow mathematical hints into speculative territory. These dreamers, as they might be called, are not reckless fantasists, but rigorous thinkers who saw connections others missed, and had the courage to propose ideas that challenged conventional thinking. Understanding their human element, their motivations and struggles, adds depth to the scientific story. Some came to the idea through pure mathematics. They were solving Einstein's field equations, exploring different configurations of matter and energy, when they noticed that black hole interior solutions resembled cosmological models. These physicists weren't looking for a radical new cosmology. They were following the math wherever it led. When it led to the possibility that our universe might be inside a black hole, they faced a choice: dismiss it as mathematical curiosity or take it seriously. Those who chose the latter became pioneers, publishing papers that others initially ignored or criticized, but that gradually gained attention. Other dreamers approached from cosmology, puzzled by features of our universe that seemed to need explanation. Why is space so flat? Why did the Big Bang begin with such low entropy? Why do fundamental constants have the values they do? Standard answers involved inflation and anthropic reasoning, but these researchers wondered if there might be a deeper explanation. When they encountered the black hole universe idea, it offered a framework where these puzzles could potentially be addressed. They became advocates not because they had definitive proof, but because the hypothesis provided new angles on old problems. The human element includes not just insight, but persistence. Many physicists who worked on this idea faced skepticism from colleagues. They were told their work was too speculative, that it strayed from testable science into philosophy. Grant applications were rejected. Papers faced harsh reviews. Academic positions became harder to secure for those whose research focused on untestable hypotheses. Yet, they persisted, driven by conviction that the mathematics was too compelling to ignore, that following general relativity to its logical conclusions mattered, even if the destination was uncertain. Among these dreamers were established scientists who risked reputational capital. Some were already well known for conventional work in relativity or cosmology. Turning attention to the black hole universe hypothesis meant diverting time from safer projects, potentially alienating peers, and facing criticism for appearing to chase wild ideas. But they made that choice because curiosity outweighed caution. They believed science advances by exploring all possibilities that mathematics allows, not just those with immediate observational tests. Their willingness to take intellectual risks inspired younger researchers to do the same. There were also younger scientists, graduate students and postdocs, who saw opportunity in the hypothesis. They recognized that groundbreaking work often happens at the edges of respectability, where established paradigms haven't yet solidified. By working on black hole cosmology, they positioned themselves at a frontier where important questions remained unanswered. Some succeeded, building careers on contributions to understanding how black holes might create universes. Others struggled, finding the academic job market hostile to unconventional research. The human element includes both triumph and sacrifice. The dreamers also include those who contributed from adjacent fields. Philosophers of science help clarify what it would mean for a hypothesis to be scientific, even if it predicts unobservable phenomena. Mathematicians develop tools for analyzing solutions to Einstein's equations in exotic regimes. Computer scientists created simulations exploring how universes might evolve inside black holes. Each brought expertise from their domain, enriching the investigation. The human element is collaborative, a network of minds working toward understanding from different angles. Women and scientists from underrepresented backgrounds faced additional challenges. Physics has historically been dominated by certain demographics, and those outside that norm often had to work harder to have their ideas taken seriously. Some who contributed to black hole cosmology did so despite systemic barriers, their persistence testament to both passion for the science and determination to participate despite obstacles. The human element includes recognizing these inequities and the strength required to overcome them. What motivated these dreamers? For some, it was pure intellectual curiosity, the desire to understand reality at its deepest level. For others, it was aesthetic appreciation of mathematical elegance, the beauty in equations that connect black holes to cosmology. For still others, it was a sense of wonder, the feeling that emerges when contemplating nested universes and infinite possibilities. These motivations aren't mutually exclusive. Most dreamers combined all three, driven by a mix of reason, aesthetics, and awe. The human element also includes moments of doubt. Even those most committed to the hypothesis experienced uncertainty. Was the work meaningful if it couldn't be definitively tested? Were they wasting years on an idea that would never be confirmed? These questions haunted many, especially during periods when research stalled or when critics were particularly harsh. The persistence through doubt is part of the human story, the choice to continue despite uncertainty, because the questions themselves were worth pursuing. There were also moments of connection and community, conferences where researchers working on related ideas gathered, shared results, and encouraged one another. Email exchanges where someone halfway around the world offered a crucial insight. Collaborations that formed between people who'd never met in person, but bonded over shared fascination with cosmic mysteries. The human element is social, built on relationships and mutual support. Some dreamers approach the work with humility, acknowledging that they might be wrong, that the universe might not be inside a black hole after all. This humility didn't diminish their commitment, but made it more authentic. They weren't dogmatic believers, but explorers willing to follow evidence wherever it led. If observations eventually ruled out the hypothesis, they'd accept that and move on. satisfied that the exploration itself had value. This attitude, combining boldness in proposing radical ideas with openness to being wrong, exemplifies scientific virtue. The human element also includes legacy. Some physicists who contributed to developing the black hole universe hypothesis have passed away, their work continuing through students and collaborators. They left behind papers, calculations, and ideas that others build upon. Their legacy is not just in specific results, but in demonstrating that asking big questions and pursuing them rigorously is worthwhile, that science at its best is adventurous and imaginative, while remaining grounded in mathematics and evidence. For those still working on the hypothesis, the human element is ongoing. They continue refining models, searching for testable predictions, engaging with critics and teaching new generations. They balance the demands of academic life, applying for grants, teaching classes, serving on committees, with the personal passion that drives their research. The human element is daily choices about how to spend time, what problems to tackle, how to communicate ideas to colleagues and public alike. Ultimately, the dreamers behind the black hole universe hypothesis remind us that science is a human endeavour. It's not just equations and observations, but people making choices about what to investigate, how to interpret findings, and what constitutes meaningful work. Their stories, with all the struggle and persistence, doubt and wonder, add richness to the scientific narrative. Understanding the human element makes the hypothesis not just an abstract idea, but a living investigation carried forward by real people seeking to understand our place in existence. Not everyone embraced the idea that we might live inside a black hole. From the beginning, the hypothesis faced opposition from scientists who saw it as untestable speculation, from those who believed it stretched physics beyond reasonable bounds, and from others who simply felt the evidence didn't warrant such radical conclusions. This opposition wasn't mere stubbornness or closed-mindedness. Much of it came from legitimate concerns about scientific methodology, from high standards for what counts as knowledge, and from alternative explanations that seemed more parsimonious. The battle for truth involves not just those proposing new ideas, but those who critically examine them, ensuring that science maintains rigour. One major source of opposition was the testability objection. Critics argued that science advances through predictions that can be confirmed or falsified by observation. The black hole universe hypothesis seemed to fail this test. Its core claim, that our cosmos exists inside a black hole in a parent universe, couldn't be directly verified. We can't see the parent universe, can't observe the exterior of our supposed black hole, can't travel beyond our cosmic horizon. Without testable predictions distinguishing it from standard cosmology, some argued the hypothesis was metaphysics rather than physics. Interesting perhaps, but outside science proper. Proponents countered that testability isn't always direct. Many accepted scientific entities, from quarks to dark matter, are inferred from indirect evidence rather than observed directly. The question isn't whether we can see the parent universe, but whether the hypothesis makes predictions about what we can see. If it implies specific patterns in the cosmic microwave background, particular values for cosmological parameters, or signatures in gravitational waves, then it's testable, even if the core claim isn't directly verifiable. The battle was over what constitutes adequate testability in cosmology, where many important claims necessarily involve the unobservable. Another line of opposition came from Occam's razor, the principle that simpler explanations are preferable to more complex ones. Standard cosmology, with its Big Bang origin and subsequent expansion, seemed simpler than invoking parent universes and black hole interiors. Why multiply entities beyond necessity? If observable phenomena can be explained without assuming we're inside a black hole, why make that assumption? Critics argued that the hypothesis added complexity without adding explanatory power, violating the parsimony principle that guides scientific theory choice. Defenders responded that what counts as simple isn't always obvious. Adding a parent universe might seem like extra complexity, but it potentially explains features like fine-tuning and low entropy initial conditions that otherwise seem brute facts. If the black hole mechanism provides a natural explanation for why our universe has the properties it does, it might be simpler in a deeper sense than models that leave those features unexplained. The debate revealed that simplicity is not a straightforward criterion, that what seems simple from one perspective might be complex from another. Some opposition focused on alternative explanations for the phenomena the hypothesis addressed. Cosmic inflation, for instance, explained the universe's flatness and homogeneity without requiring black holes. The Anthropic Principle addressed fine-tuning by noting we necessarily observe a universe compatible with our existence. Dark energy accounted for accelerated expansion. Critics argued that we already had adequate explanations for the puzzles the black hole universe hypothesis claimed to solve. Why introduce a radical new framework when existing theories worked? Proponents pointed out that existing explanations had their own problems. Inflation required specific initial conditions and left questions about what triggered it. The Anthropic Principle seemed unsatisfying to many because it didn't explain why a life-permitting universe exists, only why we observe one. Dark energy remained mysterious, its nature unexplained. The black hole hypothesis offered a unifying framework potentially addressing multiple puzzles simultaneously. The battle was between piecemeal solutions to individual problems and a comprehensive framework attempting to connect them. Opposition also came from concerns about where physics was heading. Some senior scientists worried that embracing untestable multiverses and nested realities marked a retreat from empiricism, a drift toward mathematical philosophy divorced from experimental grounding. They'd built careers on physics as an empirical science where theory must answer to observation. The black hole universe idea seemed to represent a different vision, where mathematical consistency and theoretical elegance could justify belief in unobservable realms. This was more than a dispute about one hypothesis. It was a battle over the nature and future of physics itself. This philosophical opposition manifested in heated debates at conferences, strongly worded papers, and public disagreements. Some established physicists used their authority to dismiss the hypothesis as unscientific. Others wrote articles warning against the dangers of unfalsifiable theories. The opposition wasn't just intellectual, but institutional, affecting what research got funded, what papers got published, and what topics were considered respectable for graduate students to pursue. Yet opposition also served a valuable function. It forced proponents to sharpen their arguments, to search harder for testable predictions to clarify what evidence would support or refute the hypothesis. Good science requires both imaginative proposals and rigorous criticism. The opposition ensured that the black hole universe idea didn't become accepted prematurely, that it had to meet high standards before being incorporated into mainstream cosmology. This tension between innovation and conservatism, between exploring new possibilities and maintaining standards, is how science progresses. Some opposition came from misunderstanding. Popular accounts sometimes oversimplified the hypothesis, leading to misconceptions that critics rightly called out. When the idea was presented as claiming black holes are doorways you could travel through, or that our universe will eventually be sucked into a singularity, physicists justifiably objected. Proponents had to work harder at clear communication, explaining that living inside a black hole didn't mean what science fiction suggested, that it was about geometric structure, not impending doom. There was also opposition from religious and philosophical quarters, though this was less about science than metaphysics. Some saw the hypothesis as undermining arguments for cosmic design by naturalizing fine-tuning. Others found it unsettling because it suggested existence had no ultimate beginning, challenging traditional creation narratives. While these concerns didn't affect the scientific validity of the hypothesis, they influenced public reception and sometimes colored how scientists themselves approached the idea. Within the opposition, different camps had different concerns. Pure empiricists rejected anything not directly testable. Instrumentalists argued physics should focus on predicting observations rather than claiming to describe unobservable reality. Scientific realists who believed our best theories describe actual reality could go either way depending on whether they thought the mathematics was compelling enough to warrant belief. The opposition wasn't monolithic, but represented diverse perspectives on what science should do and how it should proceed. The battle for truth continues. No definitive observation has settled whether we live inside a black hole. The hypothesis remains viable but unconfirmed, accepted by some researchers and rejected by others. This ongoing debate is healthy. preventing premature consensus while keeping the question alive. The opposition ensures that if the hypothesis eventually gains broader acceptance, it will be because it's earned that acceptance through accumulating indirect evidence and surviving sustained criticism. What the battle ultimately reveals is that truth in cosmology is not simple. We're asking questions about the entire universe's structure and origin, about realms potentially forever beyond observation. Answering such questions requires both boldness and caution, imagination and rigour. The opposition to the black hole universe hypothesis, even when wrong in particulars, serves the essential function of maintaining these standards. The battle for truth is not between those who know and those who don't, but between different visions of how to pursue knowledge at the frontiers, where observation, mathematics and philosophy intertwine. Sometimes understanding comes not as a sudden revelation, but as a gradual awakening, a slow recognition that the world is different than we thought. For those who seriously engage with the possibility that we live inside a black hole, this awakening transforms how they see reality. It's not that daily life changes. The stars shine the same way. Gravity pulls as always, and the rhythms of existence continue. But the context shifts, the frame expands, and what once seemed like the totality of everything becomes one part of something larger. This awakening is both intellectual and emotional, changing not just what we think, but how we feel about our place in existence. The awakening begins with recognizing that horizons are real. We tend to think of the universe as limitless, stretching forever in all directions. But the cosmic horizon, the boundary beyond which light hasn't had time to reach us, is an absolute limit. We will never see beyond it, not because our telescopes aren't powerful enough, but because the structure of space-time prevents it. This recognition changes everything. The universe isn't infinite, it's bounded. We live in an observable bubble, a finite region separated from whatever lies beyond. Accepting this is the first step in the awakening. From there comes the realization that this horizon might not be arbitrary, but fundamental. Not just an observational limit, but an event horizon, the boundary of a black hole. If true, then everything we observe, every galaxy, every star, every particle exists within an enclosed structure. The awakening is understanding that we're not in an unbounded cosmos, but in a bubble, potentially one among countless others. This doesn't make the universe smaller in any practical sense. It remains vast, beyond human comprehension, but conceptually it shifts from infinite to finite, from all there is to one among many. This awakening brings a sense of humility. Humanity has repeatedly discovered it's not at the center of things. Earth isn't the center of the solar system. The sun isn't the center of the galaxy. Our galaxy isn't special among billions. Each discovery has been humbling, shifting our perspective from central to peripheral. Recognizing we might live inside a black hole is another such shift. Our entire universe, vast as it is, might be one bubble in a larger structure. We're not just one planet among many, or one galaxy among billions, but potentially one universe among countless nested realities. The awakening is accepting this radical decentering, yet alongside humility comes a strange sense of connection. If universes are born inside black holes, then every black hole we observe might contain a cosmos. The stellar remnants scattered through our galaxy, the supermassive giants at galactic centers, each could be home to universes with their own histories, their own potential for life. We're not isolated, but connected through these structures. The awakening is recognizing that existence is more populated than we imagined, that reality is teeming with nested layers, each complete unto itself, yet part of a larger whole. This awareness changes how we think about time. The Big Bang, once the ultimate beginning, becomes a local event, the moment when our bubble branched off. Time in our universe began there, but time in a larger structure continued. The awakening is understanding that beginnings are relative, that what seems like the origin from one perspective is a transition from another. This doesn't make our history less real, but embeds it in a larger context. We're not living in the only timeline, but in one timeline nested within others. The awakening also touches the nature of knowledge itself. We're accustomed to thinking that Given enough time and effort, everything can be known. But if we're inside a black hole, some truths are permanently beyond reach. We cannot observe the parent universe, cannot verify our origin directly, cannot cross horizons to see what lies beyond. This recognition is humbling, but also liberating. It sets realistic boundaries on what we can know while opening imaginative space for what we can infer. The awakening is accepting both the power and limits of science. For some, this awakening brings existential questions into focus. If our universe is one among many, does it diminish the significance of our lives? Does it matter what we do if countless other universes exist? These questions mirror ancient philosophical puzzles about meaning in an infinite cosmos, but the black hole framework gives them new urgency. The awakening for many is discovering that significance doesn't require uniqueness. Our lives matter here, in this universe, regardless of how many others exist. Local meaning doesn't depend on global exclusivity. Others find the awakening spiritually resonant. The idea that universes give birth to universes, that creation is ongoing rather than finished, suggests a cosmos more dynamic and generative than traditional pictures allowed. For those with religious inclinations, it can be incorporated into theological frameworks emphasizing continuous creation. For secular thinkers, it offers a naturalistic sense of wonder, a recognition that existence perpetuates itself through physical processes. The awakening is finding that science can enrich rather than diminish a sense of the sacred. The new awareness also changes how we view black holes themselves. Instead of being merely exotic objects, endpoints where matter disappears, they become portals, gateways to new realities. This reversal, from destruction to creation, from ending to beginning, transforms their metaphorical meaning. Black holes are no longer cosmic monsters, but cosmic wombs. The awakening is seeing them not as darkness, but as sources of light, not as death, but as birth. This shift in perspective influences how scientists approach their work. Those who've undergone the awakening pursue research with a sense of participating in something larger. Measuring cosmic parameters isn't just cataloguing facts, but uncovering clues about our origin. Studying black holes isn't just understanding one phenomenon, but investigating the mechanism of cosmic reproduction. The awakening gives their work deeper meaning, connecting daily research to profound questions about existence itself. The awakening is also about accepting mystery. Even if we confirm we're inside a black hole, deeper questions remain. Why do black holes create universes? What determines the properties of child universes? Is there a first universe, or an infinite regress? These questions might not have answers, or their answers might generate new mysteries. The awakening is becoming comfortable with this open-endedness, recognizing that understanding deepens rather than resolves mystery. For humanity broadly, the awakening, if it spreads beyond scientists to general consciousness, could reshape culture. It would join other great shifts in perspective: heliocentrism, evolution, the vastness of cosmic time, as moments when we recognized our place in reality more accurately. Art, literature and philosophy would grapple with nested universes and black hole origins the way they've grappled with previous cosmological revolutions. The awakening would become part of our civilizational narrative, the story we tell about who we are and where we come from. But even for those who never fully embrace the hypothesis, engaging with it can spark a partial awakening. It opens minds to possibilities beyond conventional thinking, encourages comfort with counterintuitive ideas, and demonstrates that reality might be stranger than we imagine. This openness itself is valuable, a reminder that our current understanding is provisional, that we're still discovering the cosmos, that wonder and mystery remain even in an age of advanced science. The awakening, ultimately, is recognizing that we live in a universe that might be inside a black hole, that this possibility is scientifically respectable, and that whether true or not, it reveals how much we don't know. It's a shift from certainty to curiosity, from seeing the cosmos as understood to seeing it as deeply mysterious. This new awareness doesn't provide all answers, but it asks better questions. And in those questions lies the path to deeper understanding. Beneath all the mathematics, observations, and theoretical frameworks lies what might be called the deepest truth, the core insight that emerges when we follow the black hole universe hypothesis to its ultimate implications. This revelation isn't a single fact, but a constellation of understandings that together reshape our conception of reality. It's the recognition that existence might be radically different from what we've assumed, that the structure of the cosmos is nested and generative, that creation isn't finished but ongoing, and that we're participants in a process far grander than our circumstances alone suggest. The first part of this revelation is that black holes are not ends but beginnings. For too long they've been understood as cosmic graveyards, regions where matter falls to oblivion, where light is trapped, where time stops. But when we consider what happens inside, when we take general relativity seriously and explore the interior solutions, a different picture emerges. The interior of a black hole is not nothingness, but a region of space-time that can expand, evolve, and give rise to structure. From outside, a black hole looks like collapse. From inside, it looks like creation. This dual nature is the key to understanding. What appears as ending from one perspective is beginning from another. This revelation transforms black holes from objects of fear into objects of creative power. They are not destroyers but generators, not graves but wombs. Every black hole in our universe might contain a cosmos, complete with its own space, time, and potential for complexity. If we live inside such a structure, then our existence is not despite black holes but because of them. We're here as a consequence of the most extreme gravitational phenomenon nature produces. The deepest truth is that destruction and creation are not opposites, but two faces of the same process. The second part of the revelation concerns the nature of universes themselves. We've thought of our universe as the totality of existence, the sum of everything that is. But if the black hole hypothesis is correct, our cosmos is one among countless others, each sealed off by horizons, each evolving according to its own conditions. Universes are not unique creations but natural outcomes of physical processes. They're as common as black holes, which means they're abundant beyond measure. The deepest truth is that existence is plural, not singular, that reality is a multiverse of nested structures rather than a single cosmic container. This realization connects to the idea of cosmological reproduction. If black holes create universes, then universes that produce many black holes spawn many offspring. Over time, the multiverse would become dominated by universes capable of forming stars and black holes, because those are the ones that reproduce. Our universe, with its particular properties, might be successful in this sense, capable of generating numerous descendants. We live in a fertile cosmos, one that doesn't just exist, but perpetuates existence through the black holes it contains. The deepest truth is that universes evolve, not biologically, but through a process resembling natural selection at cosmic scales. The third part of the revelation involves the nature of time and beginnings. We've treated the Big Bang as the ultimate origin, the moment when everything started. But if our universe is inside a black hole, the Big Bang was not the beginning of time itself, but the beginning of our time, the moment when our region of space-time separated from a larger structure. Time before the Big Bang existed in the parent universe, though it's forever inaccessible to us. This means beginnings are relative, not absolute. Every Big Bang is a local event in a larger temporal context. The deepest truth is that time, like space, is nested, with timelines branching off from one another through black hole formation. This challenges the notion of a first cause, the idea that everything traces back to a single origin. If universes create universes through black holes, the chain might extend infinitely into the past with no ultimate beginning. Or it might be circular, with universes giving rise to one another in a cycle. Either way, the deepest truth is that existence might be self-sustaining, requiring no external creator or initial cause. It simply is, perpetuating itself through physical processes we can describe mathematically. The fourth part of the revelation concerns horizons and the limits of knowledge. Event horizons are not merely boundaries in space, but fundamental features of reality that separate causally disconnected regions. Our cosmic horizon plays this role, dividing what we can observe from what we cannot. This means some truths are structurally inaccessible. We can infer that a parent universe might exist, can model how our cosmos formed inside it, but we can never verify these claims directly. The deepest truth is that reality extends beyond what any observer can know, that the totality of existence exceeds any local perspective, and that profound truths might remain forever beyond empirical reach. This doesn't make such truths irrelevant. Even if we can't verify the parent universe directly, understanding our possible origin as a black hole interior changes how we interpret observable phenomena. It provides context for features like cosmic flatness, low entropy initial conditions, and fine-tuned constants. The deepest truth is that knowledge comes in degrees, that some things can be inferred even if not observed, and that theoretical reasoning can extend understanding beyond immediate perception. The fifth part of the revelation involves the holographic principle and the nature of information. If our universe is inside a black hole, then according to the holographic principle, all the information describing our cosmos might be encoded on the cosmic horizon. What we experience as three-dimensional space filled with matter and energy could be a projection from information arranged on a two-dimensional boundary. This suggests that dimensionality itself is emergent, that the apparent depth of reality arises from information processing at horizons. The deepest truth is that space and time are not fundamental but constructed from something more basic, perhaps information or quantum entanglement. This revelation challenges our intuitions about what's real. If we're holograms, projections from boundary data, does that make our experience less real? The answer seems to be no. The hologram is real. It's just that reality has a structure deeper than surface appearance suggests. Tables and chairs are real even though they're made of atoms which are made of quantum fields. Similarly, our three-dimensional world is real even though it might emerge from information at a distant horizon. The deepest truth is that reality is layered, with each layer as real as any other, but with deeper layers being more fundamental. The sixth part of the revelation is about meaning and purpose. If we're one universe among countless others, if our existence is the result of a black hole in a parent cosmos, does that give our lives meaning or rob them of it? The deepest truth here is ambiguous, open to interpretation. Some might feel diminished, seeing our universe as merely one bubble in an endless froth. Others might feel connected, part of a grand generative process. Still others might recognize that meaning is local, created by conscious beings within their contexts, not dependent on cosmic uniqueness. What the revelation offers is perspective. It shows that existence is more robust than we imagined, that creation is ongoing rather than finished, that the universe we inhabit, vast as it is, might be part of something vaster still. This doesn't answer every question about purpose, but situates us in a cosmos that's dynamic, creative, and possibly eternal. The deepest truth is that we're participants in a process of cosmic reproduction, that our lives unfold within a structure that connects us to realities beyond our horizon, and that the significance we create here matters regardless of how many other universes exist. The final part of the revelation is about wonder itself. The possibility that we live inside a black hole, that universes nest within universes, that reality is far stranger than common sense suggests, awakens a sense of awe. This wonder is not merely emotional but cognitive, a recognition that the cosmos exceeds our imagination. The deepest truth is that reality is mysterious, that our best theories point towards structures we can barely grasp, and that this mystery is not a gap in knowledge to be filled but a permanent feature of existence. We can understand more deeply, but the depth has no bottom. We can know more fully, but fullness remains incomplete. The revelation is that wonder is appropriate, that the universe deserves our awe, and that this sense of the sublime connects us to truth even when truth exceeds our comprehension. After absorbing the possibility that we live inside a black hole, after considering the evidence and implications, a moment comes for reflection. Not more analysis or theorizing, but quiet contemplation of what it all means. This reflection is personal, different for each individual, touching on questions that science alone cannot answer. What does it mean to exist in a nested reality? How should we live knowing our universe might be one among countless others? What value do our actions and experiences have in such a context? These are not scientific questions but human ones, arising naturally when cosmic understanding deepens. The first thing to ponder is scale. We're accustomed to thinking of ourselves as small, tiny organisms on a minor planet, orbiting an ordinary star in one galaxy among billions. The black hole universe hypothesis adds another layer to this smallness. Not only are we small within our universe, but our entire universe might be small within a larger structure, enclosed in what appears from outside as a compact object. This nested smallness could be overwhelming, yet there's another way to see it. We exist at a middle scale, neither the smallest nor the largest, connected to both. We're made of atoms, which are made of particles which might be excitations of quantum fields. We inhabit a universe which might be inside a black hole, which is in a larger cosmos, which might itself be nested. We're in the middle of a chain extending both inward and outward. The meaning here is connection rather than insignificance. Pondering our place in this nested structure also raises questions about uniqueness. If countless universes exist, is ours special in any way? The answer depends on what we mean by special. Our universe has properties that allow stars, planets, and life. In that sense, it's special within the subset of all possible universes, but it's likely not the only such universe. Others with similar properties probably exist elsewhere in the multiverse. This makes our universe typical among life-permitting universes, while still being one of the rare ones where complexity arises. The meaning shifts from absolute uniqueness to membership in an important category. We're not the only ones, but we're among the fortunate ones. This reflection also touches on the nature of home. If our universe is inside a black hole, is it less our home than if it were freestanding? The answer seems clearly no. Home is where we are, where we've evolved, where our history unfolds. The larger context doesn't change the immediate reality of our existence. Earth is still our planet, the solar system still our neighborhood, the Milky Way still our galaxy, the universe is still our cosmos, regardless of what it's inside. The meaning here is that home is defined by experience and belonging, not by cosmic status. We're at home in this universe because it's where we live, where we find meaning, where our stories take place. Pondering the black hole universe also invites reflection on time and mortality. If our universe will eventually grow cold and empty, if entropy increases toward a state of maximum disorder, what does that mean for the long-term significance of anything we do? This question isn't new. It's plagued philosophers throughout history. But the black hole framework adds a twist. If black holes in our universe create new ones, then our cosmos, even as it fades, might spawn countless descendants. Existence continues, not here but elsewhere, not in our timeline but in others. This doesn't make individual mortality less real, but it suggests that existence as a whole endures. The meaning might be found in being part of a continuing process, a link in a chain that extends beyond our personal or even cosmic lifespan. Another aspect to reflect on is knowledge and wonder. The black hole universe hypothesis reminds us that reality is mysterious, that our understanding is incomplete, that some truths might be forever beyond reach. This could be frustrating, a reminder of our limitations, or it could be liberating, an invitation to embrace mystery rather than fearing it. The meaning here is about how we relate to the unknown. Do we need certainty, or can we be comfortable with probability and inference? Do we require all answers, or can we find satisfaction in asking good questions? Reflection suggests that wonder might be more valuable than certainty, that living with questions can be richer than possessing all answers. The hypothesis also invites reflection on human achievement. Science has brought us to the point where we can seriously consider that our universe is inside a black hole. This represents centuries of effort, countless individuals contributing pieces to our understanding. From ancient astronomers tracking planetary motions to modern cosmologists analysing the cosmic microwave background, the accumulation of knowledge is a remarkable human accomplishment. The meaning here is about what we're capable of when we work together across generations. We've gone from wondering about lights in the sky to contemplating nested realities and black hole origins. This progression shows that human curiosity and reason can reach beyond immediate experience to grasp cosmic truths. Yet reflection also demands humility. For all our progress, fundamental questions remain unanswered. We don't know what dark matter is, what dark energy is, whether we're inside a black hole, or whether other universes exist. We don't know why there's something rather than nothing, why the laws of physics take their form, or whether existence has ultimate purpose. The meaning here is that understanding deepens but never completes. Each answer reveals new questions. Each horizon crossed reveals another beyond. The deepest truths might always exceed our grasp, not because we're inadequate, but because reality is inexhaustibly rich. Reflection on the black hole universe also touches ethics. If our universe is one among many, does that change our moral obligations? Are our responsibilities diminished because countless other beings might exist in other universes? The answer seems to be no. Ethical obligations are local. We have duties to each other, to future generations, to the life and ecosystems we share this planet with. The existence of other universes doesn't change these responsibilities. If anything, recognizing we're part of a larger structure might deepen ethical awareness. We're stewards not just of Earth or even our universe, but participants in a cosmic process that generates realities. How we act ripples through our cosmos, and potentially into others through black holes we contribute to forming. The meaning is that ethics matters locally while resonating cosmically. Pondering the meaning also involves considering how this knowledge should affect daily life. Should we live differently knowing we might be inside a black hole? For most people, the answer is probably no. We still need food, shelter, connection, purpose. The rhythms of daily existence continue regardless of cosmic context. But perhaps there's a subtle shift in perspective. Knowing our universe might be nested inside others can make us more aware of scale, more appreciative of the unlikely fact that we exist at all, more comfortable with mystery. These shifts don't change what we do, but might change how we experience doing it. Finally, reflection leads to gratitude. However it happened, whether through a black hole in a parent universe or through some other process, we exist. We're conscious beings able to contemplate the cosmos and our place in it. We can experience beauty, form relationships, create meaning, and contribute to the ongoing story of existence. The universe, whether inside a black hole or not, has given rise to us. This seems worth celebrating, worth protecting, worth passing on to future generations. The meaning, ultimately, is found not in cosmic status, but in the miracle of being here, aware and wondering, participants in the grand mystery of existence. As we come to the end of this exploration, it's worth pausing to consider what endures. The question of whether we live inside a black hole remains unanswered, and it may always remain so. Direct confirmation might be impossible, trapped beyond horizons we can never cross. Yet the investigation itself leaves a legacy, a lasting impact on how we think about the universe, how we approach knowledge, and what we consider possible. This closing isn't an ending, but a return, a loop back to the wonder that began our journey, enriched now by everything we've considered along the way. The legacy of the black hole universe hypothesis is not dependent on its truth. Even if future observations rule it out, even if we discover our cosmos has a completely different origin, the value of the investigation remains. It pushed physicists to think more carefully about horizons, to explore the implications of general relativity more fully, to develop tools for dealing with unobservable phenomena. It forced conversations about testability, about what makes a theory scientific, about the relationship between mathematics and reality. These conversations improved science as a whole, sharpening arguments and clarifying standards. The hypothesis also leaves a legacy in how we understand black holes themselves. By seriously considering that they might create universes, we've transformed them from exotic objects studied for their own sake into potentially central players in cosmic structure. This shift in perspective has motivated research, inspired new models, and connected black hole physics to cosmology in ways that wouldn't have happened otherwise. Whether or not black holes actually birth universes, treating them as if they might has enriched our understanding of what they are and what they can do. For the broader public, the legacy is cultural. The idea that we might live inside a black hole has entered popular consciousness, appearing in articles, documentaries, and conversations. It's challenged people to think beyond common sense, to accept that reality might be stranger than everyday experience suggests. This cultural shift, making people more comfortable with counterintuitive physics, benefits science communication generally. When the next surprising discovery emerges, the public will be better prepared to engage with it, having already grappled with nested universes and cosmic horizons. The return, in this closing, is to wonder. We began by acknowledging the astonishing possibility that our cosmos might be a black hole interior. We've followed the mathematics, examined the evidence, considered the implications, and reflected on the meaning. Now we return to that initial sense of awe that deepened. Wonder at the beginning was about possibility, about what might be. Wonder now is about the richness of reality, about how much we've learned and how much remains mysterious, about the fact that such questions can even be asked and partially answered. This return to wonder is also a return to humility. The investigation has shown us the limits of knowledge, the horizons beyond which we cannot see, the questions we might never definitively answer. This humility isn't defeat, but realism. It acknowledges that we're finite beings in a vast cosmos, that our perspective is local, that our understanding is incomplete. Yet, within these limits, we've achieved remarkable things. We've mapped the observable universe, measured its age and composition, developed theories describing its evolution. We've gone from primitive wonder about lights in the sky to sophisticated wonder about nested realities and black hole origins. The return to humility includes pride in how far we've come. The legacy also includes inspiration for future generations. Students learning cosmology today encounter the black hole universe hypothesis as one possibility among others. For some, it sparks fascination, drawing them into physics because they want to help answer these cosmic questions. The hypothesis serves as a gateway, showing that fundamental mysteries remain, that there's still work to be done, that science is alive and exploring, rather than finished and catalogued. This inspirational legacy might be the most important, ensuring that curiosity continues, that investigation persists, that wonder drives the next wave of discoveries. As we return to the opening tone of quiet contemplation, it's worth noting that nothing in daily life has changed. The sun still rises, gravity still pulls, time still flows forward. But the context has shifted. We now know that the familiar cosmos we inhabit might be inside a structure we can barely conceptualize, that our universe might be one among countless others, that black holes might be gateways rather than graves. This knowledge, even if uncertain, colors everything. When we look at the night sky, we're not just seeing stars, but potentially seeing the interior of a vast structure that contains us, seeing across a space that might be bounded by horizons we'll never reach, seeing into a past that might connect to larger realities. The return is also to the everyday, to the immediate. Cosmic questions are fascinating, but life happens here, in specific places and moments. The black hole universe hypothesis doesn't change the fact that we have work to do, relationships to nurture, challenges to face. It doesn't solve personal problems or provide moral guidance. What it offers is perspective, a reminder that we're part of something larger, that existence extends beyond our individual concerns. This perspective can be grounding, helping us see our troubles as local and temporary, while still taking them seriously. It's a balance between cosmic awareness and practical living. The legacy of this exploration includes the recognition that science and wonder are compatible. Too often, they're portrayed as opposites, science explaining away mystery, reducing the universe to equations and mechanisms. But the black hole universe hypothesis shows that science can deepen mystery, can reveal layers of reality stranger than any myth. The legacy is a union of rigor and imagination, of mathematics and awe, of evidence and wonder. This union is what makes science not just useful, but meaningful, not just effective, but beautiful. As we close, we acknowledge that the investigation continues. New telescopes will come online, new observations will be made, new theoretical tools will be developed. Perhaps one day evidence will emerge that strongly supports or refutes the hypothesis. Perhaps it will remain forever in the realm of plausible but unconfirmed. Either way, The question will endure because it touches something fundamental, our desire to understand where we came from, what we're part of, and what lies beyond the horizons that bound our vision. The return, finally, is to you, listening to these words, contemplating these ideas. You've travelled with me through black holes and horizons, through mathematics and philosophy, through evidence and speculation. You've considered the possibility that everything you know exists inside a structure too vast to fully comprehend. Whether you embrace this idea or remain skeptical, whether you find it unsettling or exhilarating, you've engaged with one of the deepest questions humans can ask. That engagement itself is valuable. It's what makes us human, this capacity to wonder about our origins, to question our place, to reach beyond immediate experience toward cosmic truth. So, as we close this exploration, we do so not with answers but with questions, not with certainty but with possibility, not with endings but with the awareness that investigation continues. The universe, whether inside a black hole or not, remains vast and mysterious. Our knowledge grows but never completes. Our wonder deepens but never exhausts itself. We return to the beginning, to that moment of first considering the impossible possibility, but we return changed, enriched by the journey. Thank you for spending this time together, drifting through the possibilities of black holes and nested universes. These thoughts are vast, but they need not be heavy. They are simply invitations to let the mind wander, to settle into curiosity, and to feel how wide reality might be. If you found this gentle exploration calming, if you'd like to join again on another journey through science and imagination, you're welcome to return. Your presence makes these quiet explorations possible, and I'm grateful you're here. For now, let the ideas soften into the background. Let the rhythms of thought fade into stillness. The universe is wide, horizons stretch beyond sight. But here and now, you are safe, you are steady, and you can rest. Whether we live inside a black hole or not, whether universes nest within universes or stand alone, this moment is real, this awareness is precious, and this journey of wandering together has been worthwhile. Good night.